So let's understand the RTOS ticking, which is actually implemented by the SysTick timer. As I mentioned before, there is a configurable item called config tick rate Hz. So that is actually mentioned as 1000 for this application. So that means the tick interrupt will be fired by the SysTick timer for every 1 milliseconds. And remember that this RTOS ticking is implemented using timer hardware of the MCU. So you can use any timer hardware of the MCU, no problem. But most of the time, SysTick timer will be used in order to implement RTOS ticking. So because SysTick timer actually belongs to the processor, right? So it is there on the ARM Cortex MX processor itself, right? So that's why that is actually used for RTOS ticking. So it doesn't matter which microcontroller you use, which is based on ARM Cortex MX architecture. So like STM32, LPC or Atmel's SAM based microcontrollers. So all these microcontrollers are based on ARM Cortex M architecture, isn't it? So they must have the SysTick timer. So that's why you can use that SysTick timer to implement the RTOS ticking. So why it is required, the RTOS ticking? Now the simple answer is to keep track of time elapsed. Now, so that is a global variable in pre-RTOS kernel source called xTickCount, and it is incremented by 1 whenever tick interrupt occurs. So let's take an example. Let's say there is a task 1, and let's say task 1 wants to sleep for 100 milliseconds, let's say. So sleeping means, let's say the task is moved out of the CPU and the pre-RTOS kernel made that task to sleep for 100 milliseconds. And for that, there is one API called vTaskDelay. So we'll explore more on this API later. But if you want to make your task to sleep without consuming any CPU cycles, then you can use vTaskDelay. And you should send an argument for that, let's say 100. That means the task 1 is made to sleep 100 milliseconds. So now it's actually the duty of the pre-RTOS to wake up this task after 100 milliseconds, isn't it? So how do you think the pre-RTOS tracks the completion of 100 milliseconds? So the answer to this question is pre-RTOS calculates the time with reference to the tick variable, that is a global tick variable that is being updated by the SysTick interrupt. So as you know, the tick count variable increments for every kernel tick, right? So if the tick rate Hz is 1000, then tick interrupt happens for every 1 millisecond, isn't it? So if tick count is incremented by 100, so that means 100 milliseconds have been elapsed, right? So this task will be woken up by checking the value of tick count at each SysTick tick interrupt, remember. So if tick count value is incremented by 100, then task will be woken up, right? So that's how the pre-RTOS tracks the time elapsed in the system. And for that, tick interrupts are very essential, which are generated by the timer peripheral, such as SysTick timer. So again, why it is required? Is there any other job of the RTOS tick? Yes, the RTOS tick, apart from incrementing the tick count, it is also used to trigger the context switch to the next potential task. Now let's see how. So whenever tick interrupt happens, the tick ISR runs, that we know. And when that ISR runs, all the ready state tasks are scanned. Now let's go to the code and explore. Let's go to the port.c and let's go to the SysTick handler. Here it is. And the first thing what happens in SysTick handler is increment the tick, right, as expected. So increment the RTOS tick. So if you go there, you can see that here it is, tick count +1, right? After that, what happens? So let's trace this increment tick. After that, so let's trace this function, and so there are various codes, need not to understand each and everything. So here you can see that it actually checks the ready task list. It actually checks the ready task list in order to find out is there any next potential task to be switched in. And if yes, then switch required will be returned with true. Here you can see that at the end it returns switch required. So it actually returns true if switch is required. So if switch is not required, then it will return false. So that means this function takes the decision of whether context switch is required or not by scanning the ready list of tasks. Alright, so the second point is all the ready states tasks are scanned determines which is the next potential task to run. And if found, triggers the context switch by pending the pendsv interrupt. So let's go back to the code, SysTick handler. So this is a SysTick handler, and here you can see that if this function returns true, here you can see that the context switch is required. So that's why the pendsv interrupt will be pended in the control register of the ARM Cortex-MX processor. So when you pend that pendsv interrupt, the pendsv interrupt will be triggered and the handler associated with that pendsv interrupt will run, and that context switch will be performed. Alright, so and here you can see that if increment tick is false, then it will just exit the ISR, that's it. But if this function determines that context switch is required, then the pendsv interrupt will be pended in the ARM Cortex-MX control register. So after that, the pendsv handler will run and it takes care of switching out of old task and switching in of new task. Great, so in the next lecture, let's understand who actually configures the RTOS tick timer, that is SysTick. I'll see you in the next lecture.